Welcome to this ASQ webinar presentation. I'm Pablo Baez with ASQ. Today we have with us Dr. Jack Revell. Dr. Revell has been a consultant to a broad range of organizations throughout the world. Clients better understand and improve their processes through the use of Six Sigma and continuous improvement tools, techniques, and methods, including lean practices. He holds a PhD in Industrial Engineering and Management from Oklahoma State University. He's the author of Quality Essentials, a reference guide from A to Z. And most notably, he's one of our most active contributors to an effort by ASQ's Body of Knowledge team to improve and expand one of our most popular web resources, the Learn About Quality area. In this series, Jack will be walking us through each of the time-tested quality tools featured in that area. And to get things started, today he'll be introducing our first series on the 7 quality control tools and giving us a sneak peek at what you'll learn in each of the upcoming installments. Thank you, Jack, for offering to help us launch our Quality Essentials tool series. Now let me get out of the way and pass this presentation over to you.
And I thank you very, very much, Pablo, and thanks not only to you but to ASQ for providing the opportunity to share this information about the various quality tools to the ASQ membership, and in fact to anyone who's interested in the use of the quality tools to help them to collect data, to analyze data, to solve problems, and reduce variation and reduce process complexity, and all of the other things that we are concerned about. And so let's start with an introduction to what the webinar series is all about. We're going to be talking about 4 quality tool groups. The one that we're doing today is on the 7QC, or quality control tools. This will be followed in short order with discussions about the 7 management and planning tools, also known as the 7MP tools. We'll have a series on the 7 supplemental tools and, of course, the 7 team support tools. But today, we start, as we always do, at the beginning, and we're going to talk about the 7 quality control tools. They are, in no particular order, data tables, Pareto analysis, scatter analysis, cause and effect analysis, trend analysis, histograms, and finally, control charts. Let's start out with a discussion of data tables. And the best way to do that is to start out with an understanding of data. To begin with, we need to know about data stratification. The purpose of stratification is to convert a heterogeneous population into a collection of homogeneous subpopulations, better known as samples. When we speak of heterogeneous, what we're talking about is groups that are composed of people or units with mixed attributes or characteristics. For example, differing genders, ages, costs, and or qualities, as opposed to homogeneous, which is composed of people or units with the same or similar attributes or characteristics. Part of data tables, of course, includes check or tally sheets. Now here's an example. Let's suppose that we have a situation, in this case what we're talking about administrative materials, and there's 4 different kinds of defects that seem to be occurring amongst our 4 suppliers, A, B, C, and D, listed across the top. And those defects, as you can see, are incorrect invoice, incorrect inventory, damaged materials, and incorrect test documentation. Now the way we've set up this tally sheet is to make it as easy as possible, user-friendly, if you will, for the person or persons who's going to be collecting the data. So when an individual is looking at the work provided by supplier A and he or she finds an incorrect invoice, they're going to put in a slash mark in the cell in the A column and the incorrect invoice row. And if they find that supplier A also has an incorrect inventory problem, a hash mark will be put in there, or for damaged material, or for incorrect test documentation. And we do the same thing not only for all the defects, but for all the suppliers as well. Let's take a simple example. Let's continue with supplier A. We have 4 slash marks in the incorrect invoice row. We have 5 in the incorrect inventory row. Let me go back. I may have misspoke. We have 4 in the incorrect invoice row, 5 in the incorrect inventory row, 3 in the damaged material row, and 1 in the incorrect test documentation row, for a total of 13 separate defects noted with respect to supplier A. We do the same thing for B, C, and D. And of course, we can also do the same kind of data collection, summarization, looking across row by row. For example, for incorrect invoice, supplier A, as we've already said, had 4 slash marks, B has 1, C had none, D had 2, for a total of 7. We do that for all 4 of these particular defects. And when we sum up the total for all the defects, 7, 9, 8, and 10, which sums to 34, that of course, unless we've made a math error, should be exactly the same as the total for all 4 suppliers with their 13, 6, 7, and 8 defects. Now, of course, this kind of thing can be done very easily using our various types of computer software, but for the purposes of introducing it to person or persons who are not familiar with the concept of data tables, better known as check or tally sheets, I thought it would be appropriate to present this so you can see what it looks like. And suppose we just said we're going to see how many different defects A, B, C, and D have. Well, that's, as you know, 13, 6, 7, and 8, as you can see at the bottom of this particular diagram. But when we talk about data stratification, what we're doing is we're stratifying it as to the type of defect. And as you can see, we've done it by 4 different defects. Vice versa, we may say we have these 4 different defects that we know are occurring. How are our suppliers doing? Well, we can see that we have 7 incorrect invoices, 9 incorrect inventory, et cetera, totaling to 34. But rather than seeing it across the board and mixing apples with oranges, what we do is we stratify it by supplier so we can see what the contribution to the defect rate is by each individual supplier. And in doing that, we have a 4-way stratification for suppliers, and in this case, a 4-way stratification for defects, with the result that we now have a better knowledge of where we want to attack our situation. We want to deal with the worst first. If you're primarily concerned with the supplier that has the most number of defects, we're going to deal starting out with supplier A. If, on the other hand, we're going to be working with the defect that has the greatest incidence or greatest frequency of occurrence, we would probably look at incorrect test documentation, although in this case they seem to be fairly equally spread across the board, very little difference between 10, 9, 8, and 7. So what we would do then, using this, we would take this information and we could use it we could analyze it further with a Pareto diagram or some other instrument, some other tool that we would want to use to help us to give a better understanding of what we're doing and where we're going. And by the way, this is making the assumption, although previously unsaid, that each of those defects is of the same cost or concern to us. If it turned out that damaged material was 10 times more important than, let's say, incorrect test documentation or incorrect invoice, which might only be 5 more. Let's say the least important one was incorrect inventory. I'm not saying that always is. I'm just saying that as an example. Then we have multiples. One might be 3 times more important than that, another 4 times, another 10 times more important. So before we start moving out of the check or tally sheet diagram, what we want to do is to make sure that we're working on the worst first. And working on the worst first takes us to our next tool, Pareto analysis. We know that trying to solve every problem at the same time is as frustrating as it is futile. The most cost-effective and logical approach to problem prioritization and selection is to focus, as I said, on the worst first. That is, identify the critical or vital few and temporarily set aside any work on the remainder, known as the trivial many. These are terms that were devised many, many years ago by Dr. Joseph Juran, one of the giants in the history of quality. And Pareto analysis provides us with that step-by-step process necessary to efficiently identify leading problems, defects, or errors. And here's what a Pareto diagram looks like. It's a vertical bar chart. In this case, it can be done horizontally, but we've got the bar chart with the defects that have the greatest frequency occurrence on the left and those with the least on the right. Now you might say, wait a second, what's that taller column with the O? That O stands for other. That's a grab bag. It might be onesies and twosies, and rather than lose that data in the diagram, what we do is we just accumulate them, and say, let's leave them there until we've been able to reduce the incidence of the leading types of defects, in this case G, E, and F, et cetera. And what we then do is move to spread out or stratify that which is in the O column and begin our analysis of that. Now we can see by looking at the vertical bar for defect G that approximately just under 100 defects have occurred, and in E approximately 50. But if you take a look at that cumulative percent line and the cumulative frequency percentage over on the right, you'll see that nearly 100 defects for G is equivalent to approximately 30% of all the defects occurring. And if you go to the far right side of the column for defect E and move up to the cumulative percent line and then make a hard right turn and go over to the right-hand axis, you can see that goes around 50%, which means that about half of all the defects that are occurring in this particular example are being contributed by defects G and E. And we can, in the presentation I make, the webinar on Pareto analysis, I go through step by step on how you can create the Pareto diagram and then make use of it to help us to better understand what we need to do, where we need to go, and that sort of thing. Now, having said all that about Pareto, it's time to talk about scatter analysis. In this case, the purpose of a scatter analysis is to examine a collection of paired, also known as bivariate, meaning two variables, data points, and this collection is known as a data pool, to determine if a predictable relationship exists between the two data sets, that is, between one variable and the other. Here we have a diagram that I've created using data that came out of a Time magazine article many, many years ago. It's called Tarnished Wings. They didn't have this diagram. I took the data that they had in there. They had two separate charts, one with the average age of the airline fleet in years, and the other chart with the maintenance expenses per hour of operation. They made no attempt to try and bring them together, but the moment I looked at them, I realized this had the makings of a scatter analysis. And so what I did is I plotted them. So for example, you can see the dot identified as D, which is Delta Airlines. And the average age of their fleet at that time looks like it was about maybe 9.5, maybe 9.25 years in age. And if you go and look at the vertical axis, it looks like their cost for maintenance expenses per hour of operation is about $360, $370. And we do the same thing plotting the bivariate data points for each of the airlines that existed at that time. The U/P was US Air / Piedmont. US Air had just absorbed Piedmont. A is American, C is Continental. Going over to the far right, N is Northwest Airlines, U is United Airlines, T is Transworld, E is Eastern, and P, way out of distance, is Pan Am. Now, as everybody well knows, Pan Am no longer exists, Eastern Airline no longer exists, etc. But what we do is we start drawing some lines in there, and I explain how all that is done in my webinar on the subject of scatter analysis. And we draw in the borders of that acute angle and then bisect that angle with a center line, and that becomes, if you've taken a course in basic statistics, our regression line, our predictive line, so that if you have an idea of how old the average age of the fleet in years, you can predict what the average maintenance cost per hour of operation is going to be. But in this particular case, you notice that if we take and stratify our data and take a look at it, we can see there's two clusters there. One has an axis, a center line that's approximately the same as the center line for the entire data set. The other, if you draw a straight line between P, E, T, U, and N, that's going to be approximately at right angles to the original center line. Now, what do you make of that? It looks like we have two separate groupings there, two separate clusters. When I presented this to Boeing engineers a few years ago, they got all excited about it because at that time, most of the airlines were actually flying Boeing aircraft. But we get into this at some great length in the webinar on scatter analysis, in addition to a rather unique application of scatter analysis to help figure out bonuses and pay scales for various persons. Now talk about cause and effect analysis, also known as the Ishikawa diagram, after the gentleman who devised the first one, also known as a fishbone diagram for obvious reasons. We have here a spine in the center that moves from left to right, with the arrowhead of the spine touching the problem box, in this case a wrong shaft diameter problem we're running into. And what we do is we position 3 boxes above and 3 boxes below the spine. Each box is for one of the 5 M's in an E: machine, method, material, measurement, men and women, and environment. And of course, then we attach all the boxes to the spine with arrows. And we use this as a basis for a discussion of what are the source or sources of the problem that exists in this particular case. And in the presentation I make on cause and effect analysis in the specific webinar on that topic, I discuss at great length a particular situation I was involved in several years ago in helping a home builder to identify a problem where they had some problems that existed before they even started building the houses, while they were trying to lay down electric lines and water lines in the basic land. There are a number of approaches to doing a cause-effect analysis, and they depend on the process improvement team's time constraints and the complexity of the problems that they face. Depending on these two concerns, cause and effect analysis has 3 approaches, all 3 of which are discussed in the webinar on cause and effect analysis. They are the random method, the systematic method, and the process analysis method. Now, there's one use of the cause and effect analysis technique that is rarely discussed, and that is the solution analysis. That presumes that we've gone through and identified the source or sources of a problem. We've done further work using force field analysis and multi-voting to identify, and by the way, both of those are discussed in one or more of the various webinars that I'm doing. We identify a particular corrective action. But before we want to implement the corrective action, we want to debug it. We want to make sure that there's no negative side effects associated with that corrective action. And so what we'll do is we'll put the potential corrective action in the corrective action box, and then the process improvement team will discuss whether or not there's any negative side effects associated with the 5 M's and the E: the machine, method, material, measurement, men and women, and environment. Simple example, if we have a person that is a heavy equipment operator, and that person, he or she has a bad cold or the flu, and the doctor has prescribed some heavy medicine for them, and it may say on the prescription, or even if it's not a prescription drug, that you shouldn't operate heavy equipment if you're taking this particular drug. That's a negative side effect that may have to do with, you could end up damaging the machine, you could mess up some material, you could injure people, you could do something to destroy the environment. So we want to do solution analysis as an effort to help make sure that the corrective action that we think ought to be used is not one that's going to have more negative effects than positive effects. And that is discussed, again, in detail in the webinar on cause and effect analysis. Now we'll look at trend analysis. These are graphs or run charts. These charts enable graphical plotting of data, and that can be either attribute or discrete data, or variable or continuous data. And by the way, you're going to see in the webinar that I do on trend analysis that you can use this for both types of data on the same chart, little technique that I've developed. And you can plot the data either as averages or as individual measurements or counts. And what you want to do is to ascertain the presence of either a positive or negative trends within the data that you've collected. And a trend chart without a lot of computation will give you that information. But of course, we also want to recognize if a data point is in or out of engineering specification or specs. So trend analysis has some very, very positive things. You know, it's not as enlightening as control charts, but it's much, much better than just looking at a collection of data in a table, because you can actually see the trends that are occurring and whether or not you've got points that are in or out of specification. Here's an example of a trend chart, the structure of what it looks like. On the vertical axis, we can plot either time or sequence, that's the x-axis, and on the y-axis, we can put the counts of the attribute or discrete data or the measurements of variable or continuous data. The blue center line represents the target specification devised by the engineers, as well as the dashed red lines that represent the upper and lower specification limits. Anything that's outside of either of those represents a violation of the requirements, and so being out of spec, as you can see, that red dot below the lower specification limit means that you may have to reject that particular item that the data was generated from. Histograms. These are used to graphically plot frequency of occurrence of either continuous data or attribute data, but within specific class intervals. What we want to do is convert a collection of data points, known as a data pool, into a frequency distribution, for example, a normal distribution curve, so as to analyze the status of the process from which the data was collected. Now here's an example that was drawn up using QI macro. This is a macro that was devised by Jay Arthur, the nowhere man, and it hitches onto Excel. If you were to go to Google and type in QI macro, come up with an offer to get a 30-day free download of QI macro, and it does every tool that I've talked about so far and many that I haven't talked about yet. Jay has put in plenty of templates there, and all you do is put your data, whatever data you have collected, in the usual Excel format, and click on the type of analysis that you want, whether it's histograms or Pareto diagrams or scatter diagrams, whatever it may be. And in LZAPO, you've got the chart that you're looking for. And you'll notice that in this histogram, we also have a superimposed normal distribution. And you can make a judgment as to whether or not the data that you've got collected in this sample is or is not normally distributed. And finally, we're going to talk about control charts. There are two major types of control charts. One grouping is for variable or continuous data, and the other is for attribute or discrete data. For the variable data, we have two major charts that are used that we talk about in the webinar on control charts. That is the X bar and R chart, which is the average value and the range, and the X chart, which is individual or measured value. For attribute or discrete data, we have four separate charts from which to choose. One is known as the NP chart. That's when what you're interested in is the number of defective units. The P chart, which is all about fraction defective. The C chart, which is all about the number of defectives. And the U chart, which is the number of defects per unit. Now let's take a look at an X bar and R chart and see what it looks like. On the top, we have the X bar chart. Again, this is for shaft diameters, and we can see that we have the upper and lower control limits plotted on there. Those are not the same as the upper and lower spec limits. The spec limits may be outside the control limits, they may be on the control limits, or they may be inside the control limits. These situations are discussed at length, again, in my webinar on the subject of control charts, and I hope you go and take a look and take a listen to that. Below the X bar chart is the R chart. That's the ranges. And if you were to draw a very light line, vertical line, from the top chart to the bottom chart for each of the various points, like point number 1, point number 2, point number 3, where you have the, let's see if I can do this here. If we draw a line, it should be a straight line like this. What we've got is a place where we can see what the average of, let's say, 5 data points is right here. And here we can see the difference between the highest value in that sample and the lowest value, and we plot that. And so you can see that you've got a chart of the averages and a chart of the variation around those averages using the X bar and R chart. In later years, a lot of people have moved from the R value to the S value, the standard deviation, because we now have considerably greater facility in calculating variation using the standard deviation than back in the days when the X bar and R chart was first devised. And now, having talked about the 7 QC or quality control tools, I'm ready to turn the discussion on this webinar back to Pablo, who will bring it to a close. Pablo, it's all yours.
Thanks again, Jack, for all your contributions to our growing body of knowledge and for providing our listeners with this great overview and teaser of our upcoming 7 Quality Control Tools series. I'm sure people are going to get a great value out of it. To learn more about Jack Revell, go to his website at revellsolutions.com, or you can also check out his book, Quality Essentials, which is published through ASQ, and that's item H1216, and you can find that on the Quality Press bookstore online. For more information on this and other quality topic overviews, we have tutorials, podcasts, downloadable templates, and webinars just like this one on our Learn About Quality area. You can also search for those in our Knowledge Center, which is asq.org/knowledge-center. And thanks again, and we hope you'll join us for our Essential Quality Tools series.